Estamos a la espera de que se acomoden, siguen entrando estudiantes al aula, así que vamos a esperar algunos minutitos. Muy bien, vamos a comenzar. Señor rector subrogante, autoridades universitarias, señor director del Instituto de Alta Investigación, cuerpo académico, estudiantes y funcionarios de gestión, invitados especiales, señoras y señores, tengan todos ustedes muy buenos días. La Universidad de Tarapacá, a través del Instituto de Alta Investigación, se complace en presentar sus más cordiales saludos a los presentes que se congregan con motivo de la charla magistral que ofrecerá nuestro distinguido invitado, profesor Brajesh Choudhary. Para entregar su mensaje en nombre de la Universidad de Tarapacá, se dirige a los presentes el rector subrogante, doctor Gonzalo Valdés González.
¿Se escucha bien? Sí, más o menos. Ok. Voy a hablar en inglés por respeto al profesor, pero quisiera darle la bienvenida a todos ustedes y especialmente a estudiantes de enseñanza media. Qué grata noticia que estén presentes, chiquillos, muy bienvenidos. Dear community, dear students, good morning. Okay, I'm going to say it again. Good morning. Good morning. We are very honored to have Professor Brajesh Choudhary, again, publicly sorry if I don't pronounce it correctly. Okay, thank you. To have him here, he's a well-known physicist, actually an authority on his field, and we are honored to have him here today. Before I introduce him with more details, I would like to say a few things. So I know David have told you a lot about the university, or at least I hope so. But this year, we obtained an accreditation for 6 years. What that means in our context means that we belong to a group of universities with high quality. Of course, among Chilean universities, if we compare with other universities, that's a different story. But with that in mind, our goal now is to reach farther and to reach better and for the best. And that's why I thank you for being here, and thank you, David, and all the colleagues that are going everywhere in the world trying to build a network, so because our objective is to go farther and increase our quality as a university. So without further ado, I'm gonna introduce Professor Brajesh Choudhary. Professor Brajesh Choudhary, Dr. Brajesh Choudhary, completed his undergraduate and master's studies at the University of Patna, achieving first rank in both in the university in both cases. Later, he earned his PhD in physics from the University of Delhi. During his doctoral studies, he spent 5 years working at the Fermi National Accelerator Laboratory from 1987 to 1991 in the fields of neutrino physics. At the time, Fermilab housed the world's largest particle accelerator until the construction of what is well known today, right? The Larger Hadron Collider, LHC, at CERN. Subsequently, he completed a postdoctoral fellowship at the University of California, Riverside. He obtained a permanent research position at the prestigious California Institute of Technology and later at the Fermi National Accelerator Laboratory. In 2004, he returned to India as a full professor at the University of Delhi, where he promoted the field of neutrino physics and served as the department director and other important administration duties. He has been involved with CMS collaboration at the LHC from the beginning, overseeing one of the major detectors at the University of Delhi. Throughout his career, he has published, wait for it, 1,973 articles in top physics journals worldwide, and currently maintain an impressive H index of 200. He has been advisor of several students as well as researchers. Currently, he serves as the spokesperson for all of the Asia on the board of directors of the CMS collaboration. Professor Choudhary is a globally renowned physicist, and he consistently ranked among the top 10 scientists in India. He has worked at 2 of the world's most advanced centers in the field of particle physics, specializing in the most groundbreaking areas in recent years. Notably, he contributed to the search of the Higgs boson and has dedicated his life to the study of neutrino physics and detectors. Currently, he serves as the spokesperson for the neutrino study throughout the entire India network until 2024. Furthermore, at CERN, he has been an active collaborator with the CMS team since the beginning, successfully engaging numerous institutions in the collaboration, for what we are thankful. His contribution has been significant, including his role as a member of the publication committee and as the spokesperson of the India. from 2017 to 2021. As of this year, he represents all of the Asia on the CMS Board of Directors. He has also served as the principal advisor to the government of India on major projects, one of only 6 such advisors in the country. His work has been a source of inspiration for generations of scientists worldwide, having supervised over 30 doctoral students and numerous postdoctoral researchers. He has played a crucial and important pivotal role in the incorporation of the University of Tarapacá, our university, into the CMS collaboration, making it the first Chilean university to join this collaborative effort. Additionally, under his guidance, our university is currently engaged in developing the GEM gas electron multipliers detector with Professor Shalini Thakur as a team leader. Let's welcome Professor Choudhary to our university. Thank you so much for being here today, and it is really an honor and a pleasure to have you. Thank you so much.
Muy bien, a continuación nos entregará sus palabras el doctor David Larose Navarrete, director del Instituto de Alta Investigación de la Universidad de Tarapacá.
Muy buenos días a todos. Como lo señaló nuestro rector, también voy a hablar en inglés por respeto al profesor. Estoy muy agradecido de que hayan venido tanto nuestros estudiantes como nuestra comunidad universitaria y, por supuesto, los estudiantes de colegio. So, Professor, for us, we are really thankful that you are here with us. You play the most important role that our university entered as the first university in CMS collaboration and CERN. CERN is the top laboratory in the world in high energy physics. So we are really thankful for that, and because not only for your achievement that has enlightened by our rector, that is impressive. Your career is something that all of us like to follow. But apart from that, you are a human being that very generous and try to in all the places try to help and try to build new networks. And for that, that we are there in the best laboratory in the world. Not only in Atlas, because Atlas was part of the Chilean cluster, and we entered with the help of Santa Maria University. But in some moment, with the rector, we like to have a vision, to have a differential factor that all the rest of universities in Chile. And we did that. We did that with the help of you. So we are really proud that you come here as a visiting professor of our university. So this means that the strength of our collaboration will be strong, and we will grow. And we have in our faculty, one of you are a former student, Professor Shalini Thakur, that are doing extremely good work at GEM. And we hope that our university will have the encourage in the future to send to our student to CERN, to send to our student to Delhi, to train in the best place in the world. So thank you very much, Professor, for this opportunity that you are giving us to be visiting professor in our university. Thank you.
Damas y caballeros, seguidamente me es grato dejar con ustedes al doctor Brajesh Choudhary del Departamento de Física y Astrofísica de la Universidad de Delhi y su conferencia Entendiendo los componentes fundamentales del universo ladrillo a ladrillo.
Good morning. Buenos dias. It's a pleasure to be here, and I must say that I'm overwhelmed with the reception that I have been given at the university. Thank you all for coming here. I will be today giving a talk on understanding the fundamental constituents of the universe, brick by brick. Go ahead.
Muchas gracias por su presencia, estoy honrado de que estén aquí y en este momento vamos a comenzar con una conferencia sobre el comprendimiento de los componentes fundamentales del universo ladrillo a ladrillo.
So first I would like to thank the authorities of University of Tarapacá, my friend David LaRose, and my student Salini Thakur for inviting me to University of Tarapacá, and I'm honored to be a visiting professor in this university.
Estoy honrado de ser un profesor visitante en la universidad y le doy las gracias al profesor David LaRose y a mi estudiante Salini Thakur por la invitación que me han otorgado.
Okay. So the first question is, what is our universe from beginning to end? So our universe, as you saw, it started with Big Bang, and today it is roughly 14 billion years old. 1 billion is 10 to power 9 years. So what happened that when the Big Bang happened, we do not know anything before that. After that, we see that here is the quantum gravity wall. That means all the four forces: electricity, magnetism, electromagnetic theory, a strong interaction which holds the nucleus, weak interaction which guides the radioactivity, and gravity. They were united. Then you see that here is the grand unification transition. So within 10 to minus 32 seconds of the creation of the universe, the gravity separated. Then we come here about 10 to minus 12 to 10 to minus 13 seconds, where electromagnetic and weak forces decouple. The first elements, deuterium, helium, and lithium, were formed around 3 minutes of the beginning of the universe. Then further more elements started at 400,000 of years. The galaxy started forming at 1 billion years, and today we are at roughly 14 billion years. Go ahead.
Comenzando por las bases, el principio de nuestro universo, que es aproximadamente 40 billones de años, comienza con el Big Bang. No sabemos exactamente qué ocurrió en este momento, pero sabemos que todas las fuerzas se combinaron y vemos fuerzas de electrones, de fuerzas débiles y de fuerzas potentes, que se combinaron para formar los elementos básicos que pueden ver en este gráfico. Sabemos que las galaxias se comenzaron a formar aproximadamente hace un billón de años.
Okay. So the experiment that we do at CERN, so this is CERN, European Organization for Nuclear Research in Geneva. This is the experiment, compact muon solenoid experiment on which we work. These are my two funding agencies from India. So the experiment we do recreates the situation around 10 to minus 13 seconds after the birth of the universe. So it is, we recreate the situation at the very beginning of the universe.
En nuestras instalaciones en el CERN, lo que hacemos es recrear exactamente qué fue lo que ocurrió a centésimas de segundo a partir del Big Bang.
So what is our universe made up of? When we talk of our universe, what is it made up of? Our universe is made up of three constituents. One is called dark energy, one is called dark matter, and the others are visible matter. Dark energy, we do not know what it is. We know the universe is expanding, but why it is expanding, we do not know. It is kind of a negative force. This is about 69% of the universe. Dark matter we know through gravity. So from the gravitational pull of the galaxies, we know that there is more matter in the universe than we can really measure. So there is gravity, so matter is there, and that we cannot see it through electromagnetic interaction, So it is called dark matter, 26%. And what we know of the universe today, including the particle physics, the astrophysics, the astronomy, everything, is rest of the 5% of the universe.
Entonces, ¿de qué está hecho nuestro universo? Pues está compuesto de componentes como energía oscura, materia oscura y la materia visible. Sabemos de la materia oscura por su empuje gravitacional y todo lo que es física, astronomía, equivale solamente al 5%.
So the human quest for the knowledge of the fundamental. This is for students, not for the professors, okay? The next 3 slides are for the students, not for the professors. So from the very beginning of the time, human being has tried to understand what is everything is made up of, what is the universe is made up of. This quest has been in both Western and Eastern philosophy. So in Western philosophy, if you go back historically, in West, most of these philosophy comes from the Greek. So the Greek philosopher and poet Empedocles, from 492 to 432 before Christ, he was one of the most famous philosophers before Socrates. At that point, he lived in the Sicilian villa, right now called Agrigento in Sicily. It was part of Greece at that time. Turkey, Italy, all was part of Greece at that time. Gave the theory of cosmogonic, the theory of origin and development of the cosmos. And he had 4 elements: water, aqua, earth, air, and fire, and called them roots. These elements are walled by forces of love and hate. With absolute love, they form an homogeneous unity. With hate, they separates them. The word atom comes from the Greek word atomus, which means individual, a notion invented by the Lucepi of Mille, which is in the present day Turkey in 420 before Christ.
Los humanos siempre buscaron el conocimiento y aquí tenemos algunos de sus fundamentos. La respuesta de qué es la materia, la búsqueda que ha dado por resultado la filosofía tanto de Occidente como de Oriente. La filosofía occidental, la primera línea filosófica representada por Empédocles, fue uno de los más importantes filósofos después de Sócrates. Él vivió en Sicilia, en lo que hoy en día es Italia, aunque en esa época era parte de Grecia. Él nos presenta su teoría de la cosmogénesis, en la cual hay 4 elementos clásicos que dividen la materia: agua, tierra, aire y fuego. A estos elementos él los llamó raíces. Cada uno de estos elementos está enlazados en una relación de amor y odio. Con amor absoluto forman la unidad homogénea, mientras que el odio los separa. Mientras ambos estén en conflicto, darán creación a todo lo material. La visión y la materia de la noción de elementos está unida por fuerzas de atracción y de repulsión. La palabra átomo viene del griego átomos, que significa lo indivisible, concepto creado por Lucepe de Millet en el 420 a.C.
So his student, Democritus, who is given the credit for inventing this idea, explained that the matter was made up of particles in perpetual motion and endowed with ideal qualities. And what are these qualities? Invisible because they are extremely small, which is right. Indivisible, as their name suggests. Today we know that atom can be divided. Solid, they had no void inside. Eternal because they are perfect. Surrounded by an empty space, which is also right. Having an infinite number of shapes that we see in different kind of elements. Go ahead.
Su discípulo, Demócritus, explicó que la materia está hecha de partículas en perpetuo movimiento y que poseían cualidades particulares. Eran invisibles por su tamaño diminuto, indivisibles como lo indica su nombre, sólidos ya que no tienen espacios vacíos, eternos ya que son perfectos, rodeados de espacio vacío y tienen un número infinito de formas.
So now, such philosophy also existed in the Indian philosophy. So in 6th century BC, slightly before Lucepi, there existed in India a philosophy system called Vaisesika. It was one of the 6 Hindu schools of philosophy from the Vedic system, and it used analytical method to study the nature of the world. It was closely associated with the Hindu school of logic called Nyaya, which dealt with the logical method. So Nyaya and Vaisesika, logical analytical concepts, they accept and apply each other method in understanding the atomistic constitution of the world. According to this school, knowledge is possible through three means: pratyaksha, direct sense and perception; anumana, logical inference; and sabda, verbal testimony. So the founder of this system is called sage Kasyapa, who wrote this Vaisesika Sutra. He is also called Kannada because he was an ascetic who used to gather grain from the ground, and he used to live very frugally.
Mientras Chipo de Mila en Sicilia filosofaba en este aspecto, en la India existía un sistema filosófico llamado Vaisesika. Es una de las 6 escuelas filosóficas del sistema ortodoxo vedeico y utiliza un método analítico para estudiar la naturaleza del mundo. Está asociado a la escuela de lógica llamada Nyaya, la cual lidia con métodos lógicos. En esta escuela de lógica y analítica se aceptan y aplican las metodologías para comprender la constitución atómica del mundo. De acuerdo a esta filosofía, el conocimiento se alcanza a través de 3 medios: Pretyatska, que es el sentido directo; Anumana, inferencia lógica; y Sabda, testimonio oral. El fundador de este sistema fue el sabio Kasyapa, quien escribió el Vaisesika Sutra. Él también es conocido como Kannada o Kannapuk, que literalmente significa devorador de átomos.
Okay. So Vaisesika espouses a form of atomism and postulates that all objects in the physical universe are reducible to a finite number of atoms. All material objects, it claims, are made up of 4 kinds of atoms: earth, water, fire, and air, and their different combination makes different material. Additionally, 5 substances: space, time, ether, mind, and soul were included. There was a concept of God, but the God did not create these things. God formed the universe out of these things. So the matter was formed from indestructible atoms. Their assemblies into visible thing is degradable, and at the end of worldly period, the atomic bonds dissolved. Then after a period of rest, reunited themselves into a new world. So there was both this philosophy in Greece as well as in India. Go ahead.
Vaisesika explica que los objetos en el universo físico son reducibles a un número de átomos. Todos los objetos materiales y sus elementos combinados dan como resultado distintos materiales. Además de los elementos ya mencionados, otras sustancias fueron agregadas, como lo son el espacio, el tiempo, el éter, la mente y el alma. El sistema es gobernado por un Dios, pero Dios no crea, solo les da forma. Por lo tanto, la materia fue creada a partir de átomos indestructibles. Su ensamblaje, sus cosas visibles, son degradables, y al final de su vida en este mundo, los lazos atómicos se disuelven, para luego reunirse y comenzar un nuevo mundo. Los griegos no tenían el monopolio sobre el átomo.
So now let's start with the atom. All the students know about the atom who study science. So atom is made up of a nucleus, an electron. This nucleus, here is a nucleus, multiple electrons in different orbits. A nucleus is made up of protons and neutrons. Go ahead.
Comencemos por el átomo. Aquí vemos un átomo y el concepto moderno de lo que es. El átomo tiene un núcleo y a su alrededor hay un electrón. Aquí también vemos un núcleo con múltiples electrones y luego un núcleo con protones y electrones a su alrededor. Estas imágenes muestran átomos de hidrógeno y de helio.
Electrons are fundamental. Electrons cannot be further divided or broken into. This is a hydrogen atom, 1 proton and 1 electron. Helium, 2 proton, 2 neutron, and 2 electron. But the protons and neutrons are not fundamental particles. They are further made up of a smaller particles called quarks and gluons. So you see here quarks and gluons. There are 6 kinds of quarks and there are 8 kinds of gluons. Gluons are the particle that travels between the quark, and they form protons and neutrons.
Los neutrones y protones están hechos de partículas elementales, como son los quarks y los gluones. Aquí pueden ver que hay 6 tipos de quarks y 8 de gluones.
So what is particle physics? Particle physics is the study of a small and indivisible. So particle physics is the study of the smallest known building block of the physical universe and the interaction among them, how they behave with each other. The focus of the study is either on a single fundamental particle or a small group of fundamental particles, but not on atom molecule making up an entire planet or a star. Go ahead.
La física de partículas es el estudio de lo pequeño e indivisible, el estudio de los bloques más fundamentales para nuestro universo y de las interacciones entre estos. El foco del estudio es una partícula fundamental o un grupo pequeño de partículas, pero no aquellas moléculas o átomos que conforman todo un planeta o una estrella.
So, what are we interested in? What are we interested in? This is an atom. This is an atom. This is nucleus. This is revolving electron. In the scale of 10 to minus 18 meter, this is 10 to power 8. Its philosophy was given by Kannada, Empedocles, Leucippe of Mille, Democritus. But the modern idea of periodic table was given by John Dalton in 1805. Then the nucleus. The idea of nucleus was given by Ernest Rutherford in 1911. Ernest Rutherford also gave the idea of proton in 1909. Nucleus is made up of proton and neutron. The idea of neutron was given by James Chadwick in 1932. The idea of electron was given by J.J. Thomson in 1897. Proton and neutrons are made up of quarks. The idea of quark was given by Gell-Mann and George Zweig in 1974 and experimentally discovered into 1968 by Richard Taylor, Jonathan Friedman, and Henry Kendall. Go ahead.
Estamos interesados en estudiar el constituyente más pequeño de la materia. Aquí pueden ver el átomo. Aquí está el núcleo, el protón, el neutrón girando alrededor del núcleo a una escala minúscula. Aquí pueden ver que la filosofía detrás de esto nos ha sido otorgada gracias a varias personas, pero los conceptos actuales fueron entregados por John Dalton. La idea del núcleo y del protón fue creada por Ernest Rutherford. El descubrimiento y la idea del neutrón fue hecho por James Chadwick en 1932. Los electrones y sus partes fundamentales fueron identificadas más tarde junto a los protones y neutrones que fueron constituidos por quarks. Ellos fueron postulados por Gell-Mann y Zweig en 1964, por lo que ganaron el premio Nobel, y descubiertos por Taylor, Friedman y Kendall en 1968.
So what I want to, this is, atom is 10 to power 8. We are looking at a scale of 10 to minus 1 or at a scale of 10 to minus 18 meter. So very, very small. One more thing for the students. J.J. Thomson's student was Ernest Rutherford. Ernest Rutherford's students were James Chadwick. So electron, proton, and neutron all were discovered in the same lab in the same family.
Aquí estamos lidiando con una escala minúscula. Y un dato interesante es que Rutherford fue estudiante de Thomson y de Chadwick al mismo tiempo. Todas las partes fundamentales que conforman el átomo fueron descubiertas en el laboratorio de Rutherford en Cambridge.
So, unification of forces. We know about gravity, we drop a ball, it goes. We know about magnet, it attracts the metallic thing. So, in 1666, Isaac Newton merged the idea of terrestrial and celestial gravity. In 1856, James Clerk Maxwell merged the idea of electricity and magnetism. They are the part of the same force. In 1960, Sultan Glasso Abdus Salam and Steven Weinberg merged the idea of electromagnetic and weak force. So we know about gravity, we know about electromagnetic force. Weak force is which guides the radioactivity. The radioactivity is guided by the weak force. And the electroweak is the electromagnetic and weak force are the manifestation of the same force at some higher energy scale. Now, the strong force which keeps the nucleus together. So, for example, a nucleus is made up of proton and neutron. Neutron is neutral, proton is positive. So, they should repel each other and they break, but they don't. So, there is some bigger force which holds them. That is the strong force. If they can be understood as part of the same force, it will be called grand unified theory, which we do not know. And if the gravity could be merged into grand unified theory, it will be called supergravity, for which we do not have the possible energy to figure it out.
En la unificación de fuerzas existen 4 tipos de unificación, y estas son terrestre y gravitacional, electricidad y magnetismo. Luego viene la fuerza débil, que tiene relevancia con todo lo que es radiación. Y podemos ver que si una fuerza débil y una potente tienen masa, es llamada la gran teoría de la unificación. Pero no tenemos medidas de energía al respecto, y la variedad sería llamada supergravedad, con lo cual tampoco hay medidas de energía para poder comprobarlo.
So fundamental particles and forces, these are the 6 quarks. 3 quarks make a proton, 3 quarks makes a neutron. These are called leptons. So these particles participate in a strong interaction, electromagnetic interaction, and weak interaction. These electron, its heavier particle, heavier cousin muon, and further heavier tau, they participate only in electromagnetic and weak interaction. There are 3 neutrinos which participate into weak interaction only. Photon is the carrier of electromagnetic field. There are 8 gluons which are carrier of the strong force. W and Z, W plus, W minus, and Z are the 3 bosons which are carrier of the weak force. So these are the fundamental forces, and Higgs is the particle by interacting with all the particles except neutrino get their mass.
¿Cuáles son las partículas fundamentales y cuáles son sus fuerzas? Aquí tenemos 6 partículas fundamentales, estos son los quarks, y hay 6 leptones. Aquí están las partículas de fuerza gamma para el electromagnetismo y gluón para fuerza alta y zeta para fuerza débil. La gravedad no está en esta imagen, ya que no es parte de la física de partículas. Pero ¿cómo es que estas partículas adquieren masa? Requieren que su masa sea atraída por lo que conocemos el bosón de Higgs.
So the properties and interaction among these particles is called the standard model of particle physics that we study. The Higgs mechanism was given in 1960s, and the electroweak theory and WZ mass prediction was done in 60s. The Nobel Prize for electroweak theory was given in 79. WZ was discovered in 83. Nobel Prize was given in 84. The discussion for Large Hadron Collider, which I will talk today, to discover Higgs started in 84. Higgs was discovered in 2012 and Nobel Prize was given in 2013.
En los años 60 se nos dio la teoría del electrón de masa débil, que fue más tarde validada en el 79. La WZ fue descubierta en el 83 y hubo grandes ganadores del premio Nobel el año 84. El colisionador de hadrones más grande fue creado e ideado en 1984. Su construcción comenzó en 1998, terminando en el 2008. El bosón de Higgs fue descubierto en el 2012 y el año siguiente recibieron el premio Nobel por este descubrimiento.
So how you see the mass of different particles and their electric charge. So they are either charged or neutral. The quarks have fractional charge. And you can see that top quark is 170 GeV, and you can see electron neutrino is of the order of 10 to minus 9 GeV. So there is a difference of 10 to 11 order of magnitude in the mass. So what happens when these particles interact with the Higgs field? By interacting with the Higgs field, the quark, the charged leptons, and intermediate vector bosons get their mass, but not the neutrinos.
Respecto a las masas de partículas, aquí tenemos que las partículas y sus varias masas generan la pregunta de cómo es que esas masas son adquiridas. Pues interactuando con el campo de Higgs, quarks, leptones cargados y sus vectores de bosón intermedios adquieren masa al contrario de los neutrinos.
So who are the people who gave the theory of the Higgs boson? In 1960, there were 3 groups of people, Anglet and Brout, then Peter Higgs, then Guralnik, Hagen, and Kibble. 3 papers were written how the particles acquired their mass through interaction with the Higgs boson, and they were all published in the same volume of the Physical Review letter. These gentlemen were in Belgium, he was in England, and these 3 were at that point of, he was in Edinburgh, and these gentlemen were working at that time in London. All the 3 gave the theory. In the same paper it was published. But when the Higgs boson was discovered, since Nobel Prize can be given to only 3 people, this gentleman had died in 2011. So these two got the Nobel Prize.
Esta es la gente que le dio vida a la teoría del bosón de Higgs. Acá tenemos grupos, aquí está Englert y Prout, Peter Higgs, Grant Hill, Hagen y Kipu. Estos 3 caballeros escribieron artículos en 1964 relacionados con el tema. Posteriormente, cuando se descubrió el bosón de Higgs, solamente Englert y Higgs fueron los galardonados con el premio.
So now let me tell you how, in a very simple term, how the Higgs boson works. So this is the Higgs field. A particle comes. This is Margaret Thatcher. So old people will remember who was Margaret Thatcher. She was the Prime Minister of England till 1990. And so this slide has been taken by a person from UCL who made it. So this is Margaret Thatcher, the Prime Minister of England comes. All the people gather around her. So there is a very strong interaction among with the particle, and that's how the particle gets the mass. So if the interaction is very strong, the particle has higher mass. If the interaction is weak, the particle has a small mass.
Permítanme explicarles cómo obtienen las partículas su masa y cómo interactúan en el campo de Higgs. Asumamos que este es el campo de Higgs, y aquí, representado por el primer ministro de Inglaterra, Margaret Thatcher, al entrar a un auditorio, atrae la atención de la audiencia. Así es como una interacción más pesada es la partícula, y la interacción del campo de Higgs es lo que le da la masa a esta.
So, electroweak theory, which unified the electromagnetic theory and the weak theory. So electromagnetic theory we know, which is about the charged particle, and weak force is about the radioactivity. Those were incorporated into the same theory called electroweak theory at a certain energy scale by 3 gentlemen, Selden Glasso, Abdus Salam, and Steven Weinberg. And this is the picture, beautiful picture of them going in 1979 to receive the Nobel Prize. Now, quantum chromodynamics, chromo means color. This is the theory of a strong interaction that holds the nucleus together, and it was given by a whole bunch of different people over different part of the time.
¿Cuál es el modelo estándar de la física de partículas? Pues esta incorpora las teorías de campos de hábiles creadas por Glasso, Salam y Weinberg, quienes recibieron el premio Nobel en 1979. Aquí pueden ver una fotografía de ellos. Y a través de la cromodinámica cuántica, la cual es la teoría que explica que mantiene al núcleo junto y que ha sido postulada por varios autores.
So now, what is the status of particle physics today? What is the status of particle physics today? We know about the particles, the quarks, lepton, gauge bosons, Higgs boson. How do they get the mass? So the theory has been very successful. All the experiment done over the last 60 years has been explained. But there is evidence of new physics beyond the standard model. We know that the universe is accelerating, it is expanding, which is the dark energy, but we do not know what is dark energy. We know that there is a missing mass, which is dark matter, but we do not know what is dark matter. We are doing the experiment, but we don't know. So these together means 95% of the universe is not known to me. They are dark to us. Then neutrinos, these 3 particles have masses and they mix with each other. Nu e can become nu mu can become nu tau. How does this happen? Where do they get their mass? We do not know. Or are there physics beyond what we know today? So there are many questions that the standard model does not explain.
Hemos estado discutiendo el estado de la física de partículas hasta el día de hoy, pero el modelo estándar ha explicado de manera exitosa la mayoría de las observaciones hechas hasta la fecha, aunque no explica del todo el porqué. ¿Qué es lo que no explica? Por ejemplo, la aceleración del universo, que es la energía oscura, la masa faltante, que es la materia oscura, masa de neutrinos y sus combinaciones, física que va más allá del modelo estándar, y que hay física más allá del modelo estándar a una escala de TeV. Para encontrar estas respuestas se utiliza el colisionador de hadrones.
So this is a slide again for the student. What are the open questions in particle physics today? Particle physics, astrophysics, cosmology. So there are 3 sectors. Cosmic sector, which we look through the telescope and we study, and Chile has old tradition of working with the telescope. energy sector, where you accelerate particles at very high energy and collide them at very high energy. So this creates the situation at the beginning of the universe. That is called the energy sectors. An intensity sector, where very large number of protons, particles strike a target, and then you study rare process. So let me frame some questions which are very important, especially for a student. What is the nature of dark energy, which constitutes roughly 3/4 of the universe? What is dark matter and how one can find it? How did the universe began? We don't know. What are the masses and properties of neutrino? We know little bit about it. What role did they play in the evolution of the universe? How they are connected to matter-antimatter asymmetry. Now, matter-antimatter asymmetry is when the Big Bang happened, the amount of matter, the amount of antimatter was equal. Today, when we look at the world, universe, we only find matter. So what happened to all the antimatter? Somehow they converted to the matter. We do not know how. Then in energy sector, are elementary particles fundamental? How do these particles acquire mass? We have found the Higgs boson, but are there further Higgs boson? What is the physics beyond this standard model? What are the new particles and their interaction? Do all forces unify at such an energy? Why there is matter-antimatter anomaly in the universe? What led to it? Why there are only 3 generations of particles? Why not 4? Why not 5? Why not 2? Why there are 3? So these 13 questions are all open questions. I do not know answer to any one of them. If anyone knows answer to it, first class ticket to Stockholm to get your Nobel Prize. And these all are connected to each other. These all are connected to each other. So it all, we work here, we also feed back here, we also feed back here.
Esto es lo que vemos por el telescopio. Aquí se ven cómo están conectados el sector cósmico con el sector de alta intensidad y el sector de energía, cómo se relacionan y interactúan el uno con el otro. Hay preguntas, 13 para ser exacto, que son de naturaleza inexplicable. Lo que queremos saber aquí es, por ejemplo, cuál es la naturaleza de la materia oscura, cómo encontrarla, cómo empezó el universo, cuál es la masa y sus propiedades y la propiedad de los neutrinos, cuál es su rol en la evolución del universo, cómo se relacionan la simetría y la simetría con la antimateria y la materia. Sabemos que la antimateria existía, pero actualmente no podemos encontrarla. Si responden a cualquiera de estas preguntas, se ganarán automáticamente un ticket en primera clase de Estocolmo para recibir el premio Nobel.
So now how do we go about doing this study? So this is the CERN, Large Hadron Collider Tunnel. This is the dipole magnet, the energy frontier, Large Hadron Collider at European Organization for Nuclear Research. It is the biggest and most powerful microscope ever made in history. Students think that microscope is something you look through it, but then there is electron microscope, and this is the most powerful microscope. It looks at a distance of nanometer times nanometer, 10 to minus 18 to 10 to minus 19 meter. A new boson was discovered in 2012, and we hope to get further particles.
¿Cuál es la frontera de la energía? Aquí pueden ver una foto del colisionador, que técnicamente es el microscopio más poderoso de la historia de la humanidad. Aquí es donde fue descubierto el bosón, y podemos apreciar parte de sus componentes, y con esto esperamos que en el futuro produzcan nuevos y mayores descubrimientos.
So how is the distance scale? This is the formula from Louis de Broglie. Energy is hc over lambda, or lambda is hc over E. So higher the E, lower the lambda. So you can see smaller distances. So visible light is 10 to minus 6 meter, electron microscope 10 to minus 10 meter, alpha particle 10 to minus 14 meter, 1 TeV proton at Fermilab 10 to minus 18 meter, 7 TeV protons somewhere between 10 to minus 18 to 10 to minus 19 meter, and that is the scale that we are working on.
¿Cuál es la escala de distancia probada? Gracias a Louis de Broglie en 1925 es que podemos ver que la onda es inversamente proporcional a la energía. Mientras más energía, más corta es la onda, y esta es la distancia a la que puede ser sondeada. ¿Qué pasa al descubrir una nueva partícula? Es que se necesita más y más energía para poder sondear distancias muy reducidas. Aquí pueden ver algunos detalles en comparación a la escala de longitud más pequeña investigada hasta la fecha.
So now we do this experiment at CERN. what is CERN? For the students, it's very important. For the professors, they know. CERN stands for European Organization for Nuclear Research. It is situated in Geneva on the Swiss-French border. It is the largest accelerator particle laboratory in the world. It provides physicists the necessary tool to explore what matter is made up of and what forces hold them together. It was founded in 1954 on 29 September. It has 23 countries as member state, and many of them are associate member. It has 2,500 scientists, technical and administrative staff, and about 12 to 15,000 people who go from all over the world to work on it. And it gets about 150,000 visitors every year. CERN is an official United Nations observer. Now, all of you use www, internet you use every day. It was discovered at, World Wide Web was discovered at CERN, okay? And this is the place where WW was discovered. Beside that, this lab has many Nobel Prizes for WNZ in 84, 1992 Novel Tracking Detector, 2013 Higgs Boson.
¿Qué es el CERN? El CERN es el Centro para el Estudio de Energía Nuclear localizado en Ginebra, en la frontera suiza con Francia, y es el acelerador más grande del mundo. Provee a los físicos las herramientas necesarias para explorar lo que hasta la fecha es la materia y cuáles fuerzas trabajaron para que ésta fuese creada. Fue fundado en 1954. Actualmente tiene 23 estados miembros y asociados y tiene más de 25.000 científicos trabajando en él, personal técnico y administrativo. Alrededor de 12.000 usuarios. Más de 130.000 visitantes van cada año a aprender sobre el bosón. Es oficialmente un observatorio de las Naciones Unidas y es el lugar de creación de la World Wide Web. Este centro ha sido galardonado con varios premios Nobel en física.
Okay. So, Large Hadron Collider, it is a proton-proton machine. You see this circle. This has a circumference of 27 kilometers. It is 100 meters underground. The construction time to build this machine and the experiment was 10 years. It has 9,300 magnets, which are dipoles. Dipoles has 2 poles. They bend the magnet because the protons are going at speed of light. So, bend that, you need very high power magnet, which is 8.3 Tesla, it bends it. Quadrupole, which focuses it at the interaction point. Sextupole, octupole, which corrects the orbit of the magnet. Magnets are pre-cooled to 80 degrees with 10,000 tons of liquid nitrogen, and then they are further cooled to 1.9 degree Kelvin with 60 tons of liquid helium. 15 institutions from India are collaborating there. University of Tarapacá is the first group of Chile, although University of Santa Maria has also joined after Tarapacá. And we work on this experiment. There are 4 experiments.
El LHL es una máquina de protón a protón. Este es un anillo de 27 kilómetros de circunferencia en el cual los protones viajan en ambas direcciones para colisionar en 4 lugares. Tiene 93.000 magnetos, diápolos, cuadrípolos, sextuplos y octúpolos. Estos magnetos son necesarios para doblar, enfocar y caracterizar los rayos de protones. Los magnetos son preenfriados a 80 grados usando 10.080 toneladas de nitrógeno líquido y luego se les enfría aún más a 1.9 Kelvin con 60 toneladas de helio líquido. Hay 15 instituciones de la India participando y actualmente la UTA pertenece al primer grupo de Chile al que se ha unido al proyecto CERN. La construcción del laboratorio duró alrededor de 10 años y está a 100 metros bajo tierra.
So, this is the CMS collaboration. All the blue countries are part of the CMS. Here you see Chile. CMS collaboration has 255 institutions from 57 countries, 6,000 active members, more than 2,000 PhD physicists, 1,100 PhD students.
Aquí pueden apreciar en azul todos los países con presencia en el CMS, incluyendo a Chile, y a 233 instituciones de 57 países. Cuenta con más de 6.000 personas trabajando, más de 2.000 físicos y más de 11.000 estudiantes de doctorado.
So, LHC timeline, I will not go into detail. I will only say that the idea of Large Hadron Collider started in 1984 after W and Z was discovered. The construction started in 1998. It was built in 2008. The discovery was done in 2012. The theory was given in 1964. So it took roughly 50 years from the theory to the idea to the machine to the discovery.
Línea de tiempo del LHC. Para no entrar en detalle, quiero destacar que se tomó alrededor de 50 años desde el concepto de la idea del CERN hasta su construcción y posterior descubrimiento del bosón de Higgs y la obtención del premio Nobel.
Okay. So this is the CERN complex of accelerators. So you do not accelerate particle to the final energy once. We start with a linear accelerator, we take it to, this is the linear accelerator, we take it to 50 MeV. Then we take it to booster, we take it to 1.4 GeV. So MeV is 10 to power 6 electron volt. 1 electron volt is when there is a voltage difference of 1 volt and the electron passes through them. GeV is 10 to power 9, TeV is 10 to power 12. So with the LINAC 50 MeV, booster 1.4 GeV, proton synchrotron 25 ZeV, super proton synchrotron 450 GeV, and then Large Hadron Collider 70 eV.
Aceleradores CERN y sus experimentos. El acelerador no es solo una máquina, es un complejo de 5 máquinas donde el protón es disparado en el número 1 con una velocidad, con una energía y velocidad, y luego pasa al número 2 donde esta es incrementada. Cada paso incrementa su energía y velocidad hasta llegar al número 5 con una energía promedio de 7 TeV.
Okay, so this is just a picture of quadrupole which focuses. There are 474 quadrupoles in total. I took it myself in 2007. This is the tunnel, and as you see, there is the collision point.
Esta es una fotografía, como pueden ver, acá están los paneles. Yo mismo he tomado esta fotografía en el 2007, y estos son módulos cuadrúpolos, los magnetos en los cuales ocurre el momento de la interacción.
This is how the picture looks. You are looking from the tunnel. Now you can't go into the tunnel because of the radiation. It has worked for so many years, so it is very hot. When there is radiation, it is called hot. And this is the detector where the interaction will take place. This is just a view.
Esta es una foto del túnel y del detector. Actualmente no se puede ingresar al túnel ya que tiene grandes cantidades de radiación.
This is the dipole magnet. It is a 15-meter long, 28-ton heavy LHC cryodipole. It works at 1.9 degree Kelvin temperature. There are 1232 of these dipoles around the beam in the ring, and their job is to bend the protons which are going into at the speed of light, and 100 billion proton goes in one bunch. It is not one proton, 100 billion proton followed by 100 billion proton followed by 100 billion proton. Go ahead.
Cada disparo de protones no va a uno, sino que millones de ellos. Este es un diaplo del LHC que trabaja a 1.9 Kelvin. Hay 1232 de estos y este tiene 12 magnetos.
So what are the main physics goals of the experiment? So we know a standard model with very high precision, but we can still know it better. So that is one thing. Search for the origin of mass. How did particle got the mass? So we know that they got their mass with the interaction with the Higgs boson, and we have discovered the Higgs boson, but there could be, other Higgs boson. Search for dark matter through the lightest supersymmetric particle. There is a theory called SUSY. The lightest particle will be the supersymmetric particle, which will be dark matter. Understand the nature of a space, time, and unification of forces. So the very beginning, Big Bang. How? You look at large extra dimension. So the universe, we know of 4 extra dimensions, x, y, z, and time t. But there are theories where there are 10 dimensions, and these dimensions are there. You can search for those. Or you can search for micro black hole. Study matter-antimatter asymmetry, or you understand the primordial plasma. So all these are the aims of the experiment.
¿Cuáles son los objetivos del experimento del colisionador? Testar el modelo estándar de alta precisión, ya que si bien hemos conocido la física desde 60 años, aún tenemos que probarla con la más alta de las precisiones. La búsqueda por el origen de la masa. Ya hemos descubierto el bosón de Higgs, pero puede que existan otros que aún permanecen en el misterio. La búsqueda por candidatos de materia oscura, por medio del descubrimiento de partículas supersimétricas livianas, que es una teoría de la supersimetría, ya que la más liviana supersimetría podría significar materia oscura, la cual iría más allá del modelo estándar y comprende más del 23% del universo. Comprender la naturaleza del espacio-tiempo y las fuerzas de unificación por medio de la búsqueda de extradimensiones y la producción de microagujeros negros en el laboratorio para el estudio del espacio-tiempo. El estudio de la simetría de la materia y la antimateria puede arrojar luz sobre el origen de este. Entender la naturaleza del Big Bang o el plasma primordial que data del principio del universo. Todos estos son objetivos de los experimentos cubiertos por el colisionador de hadrones.
This is just a picture. University of Chile Tarapacá is working on 2 experiments. One is called Atlas, which Sonia Cabana is leading. One is called CMS, which Salni is leading. This is a 4-story building in CERN where our office is. And this just shows you that this big one is the Atlas detector. This one is the CMS detector. What we need in these detectors are track the particles to a very fine precision as far as position is concerned, their angle is concerned, their bending is concerned. We measure their energy in electromagnetic calorimeter and hadronic calorimeter. There are muons come from cosmic ray but also produced in proton-proton interaction. So the muons will go through it, and we have to have magnetic field to bend these particles so we can distinguish from charged particle and neutral particle.
Aquí una representación de los detectores en los que trabajamos. Miden aproximadamente 4 pisos de altura y este es el edificio en el que trabaja la doctora Chalini y el doctor Larose. Este es el detector llamado Atlas y el segundo es llamado CMS. Ambos son detectores con propósitos generales. Ambos rastrean partículas que miden electromagnetismo y energía llamado calorímetro. Buscan muones, partículas que viajan por distancias prolongadas y miden campos electromagnéticos.
So this is the comparison of 2 detectors. One detector is larger in length, but this has more iron, so it is compact. That's why it is called compact muon solenoid. You see this is 7,000 ton, this is 13,000 ton. So this is just a comparison to show to the students it is the heaviest ever machine and it has more iron than Eiffel Tower. Okay?
Acá podemos ver una comparación de ambos detectores, el Atlas y el CMS. Una comparación interesante es de que el CMS tiene tanto hierro que podría ser incluso superior al que hay en la Torre Eiffel.
So what are the experimental challenges? When you are doing the experiment, what are the challenges? There are various challenges. 100 billion proton collides each one. So there are 40 million crossing per second. And each crossing has 25 interactions. So you have 1 billion proton-proton interaction every second. But your electronics can only write few times 100 interaction out of 40 million crossing. So you have to trigger them and you have to make sure that you only write important physics events, and your electronics need to be very fast as well as the storage of the electronics while you make the decision. So this is the challenging part.
¿Cuáles son los desafíos de estos experimentos? Para empezar, tienen un rango de interacción muy amplio. Millones y millones de protones son disparados por ambos lados, creando 40 millones de cruces por segundo. 20 a 25 interacciones por cruce y esto equivale a 1 billón de interacciones por segundo. Los datos solo pueden detectarse a una rata de 100 cada 40 millones de cruces. Por lo tanto, hay que hacer una selección de interacciones y eventos que duran microsegundos. Es necesario tener equipos que almacenen esta información para realizar todas estas interacciones.
So this slide I am going to skip, David, this one. Okay? So this is the compact muon design. This is the cut view of the detector we work. So this one, purple, is made out of silicon. It is a tracker which has 75 million channels. 75 million channels of electronics. This is electromagnetic calorimeter made out of lead iron tungstate. This is hadronic calorimeter which is made out of brass and scintillator. And then these red ones are further this white one is the solenoidal magnet, and in which everything is wrapped around. Outside these are further iron, which have magnetic field, and yellow ones are different kind of muon chambers, one of which is the gem detector. This is the old picture, current one on which we are working.
Este es el detector donde la doctora Colaros y yo trabajamos. Esta es una vista seccional y muestra que la parte púrpura está hecha de sílica y rastrea la partícula. La partícula cargada puede ser rastreada desde aquí. La parte blanca es el magneto en donde la partícula cargada se curva, mientras que la neutra no. La sección del calorímetro electromagnético está en verde y hay una sección del calorímetro electromagnético en púrpura. Las secciones rojos son magnetos y los amarillos son 4 tipos distintos de detectores de muones, donde desde su dirección podemos medir la interacción de estos.
This is just a broken down view of the same detector as it looks like. This is the solenoid. These are the muon system. Inside of it is hadronic calorimeter, electromagnetic calorimeter, and the silicon tracker. You can see its total weight is 13,000 ton. Diameter is 15 meter. Overall length 21 meter. And the magnetic field is 4 Tesla.
Estos son los solenoides magnéticos durante la construcción del colisionador. Esto tiene un peso de 2.000 toneladas y fue bajado a su posición actual desde una altura de 100 metros en el 2007. Estos detectores no están hechos de una sola pieza, sino de múltiples, y están ensambladas, y pueden aquí ver dónde los rastreadores de muones son localizados en distintas partes. La energía es depositada y la circulación que llevan es relevada en los 4 detectores.
The detector was built at the surface, and then it was lowered in 11 pieces, 100 meters down.
El detector fue construido en 11 piezas y fue bajado en 11 piezas a 100 metros bajo tierra.
So this is just a picture. Here on the top is the surface. This is 100 meters down. The detector is down there. You can see that this is the hole to take the detector. This one is the solenoid. This is 2,000 tons of iron. And it was lowered from top to bottom, and the margin on each side was barely 1 inch. So 2,000 ton is going down. You just think of that if it has a small twist, everything will go away. So it was in February 2007, it was successfully lowered down and then assembled there.
En febrero del 2007 fue bajado este solenoide hasta su posición actual. El margen de error era de 1 pulgada por extremo. Este hito requirió la precisión de ingeniería única.
These are some of the nice pictures just. This is the silicon tracker. You can see that the end cap, tracker end cap is there. There are different views. You can see there are 3 sections of the silicon tracker. They are all being done. So when finally assembled, it looks like this. It has 75 million channels of silicon strips. So you have to read those 75 million channels.
Estas son imágenes de las placas de rastreo de silicón que tienen una resolución de 65 millones de píxeles. Esto permite la medición de partículas a un nivel de micrones y pueden apreciar aquí varias partes de este.
This is how one end was completely lowered, and this was featured on the front page of the Science magazine.
Aquí pueden ver una imagen de cómo era el colisionador mientras estaba siendo bajado hasta su posición actual. Y esta imagen finalmente fue la portada de la revista Science.
And this is how the detector looks. It's like a cylindrical thing when everything is closed. One proton will come from this side, proton will come from this side, and in the middle of the detector they will collide.
Esta es la posición final del detector y actualmente luce como un cilindro. Aquí es por donde se emite un protón, hay otro protón que sale desde la otra salida y interactúan en el centro de este.
I would like to tell the students that it is not 1 or 2 protons that comes. In each bunch, there are 100 billion protons, and after 25 nanoseconds, so you can multiply the velocity of light with 25 nanoseconds, and there is another bunch of proton. It keeps following. So in the total accelerator, there are more than 2,000 bunches of 100 billion proton going from one direction and other direction, and they collide.
Cabe destacar a los estudiantes de que hay más de 100 millones de protones que son disparados por cada extremo y hay más de 50 millones de interacciones entre ellos. Pueden hacer los cálculos físicos según los datos que tienen.
So now how do we know which particles are coming out? So this is a sliced view of the detector. You see this is a particle which goes through the tracker. Magnetic field is here, but it does not bend. It's a straight line. That means it is a neutral particle which deposited energy in the calorimeter. This is a charged particle because it has a bend and you see it deposits energy. So these are this is photon, this is electron. This is a neutral hadron, whereas this is a charged hadron because you see it has a curve and it deposits energy into the hadron calorimeter. And this is a muon which goes through this one bend and another bend, and these are the muon chambers. So that is how we distinguish the different particles in the detector.
¿Cómo es la interacción de partículas y su detección? Esta es otra vista del detector y aquí podemos ver los distintos tipos de partículas. Algunas partículas no se curvan y estos son llamados neutrones. Algunas partículas se curvan como las partículas cargadas. En este sistema, el muón, el cual va por el detector interno y externo, el calorímetro electromagnético y el calorímetro del tambor. De esta manera sabemos que un fotón, si es un electrón o un muón, y cuál es la energía electromagnética y otras mediciones.
So what are the challenges in detector construction? Large area detector, high resolution, so position should be measured in micron, time in nanometer or smaller, nanosecond, sorry, and energy precision should be very high. So it is needed for triggering. It should be radiation hard because protons are coming, and then you should have high voltage, low voltage, all of that. So I will not go into software, but electronics should be fast, radiation high, hard, high granularity, very small, miniaturization with ASIC and FPGA. ASIC is a specific application, a specific integrated circuit. FPGA is field programmable gate array integrated circuit. So you have very high-end integrated circuit that you need.
¿Cuáles son los desafíos que tienen los equipos y los detectores? Estos detectores tienen que existir en un área considerable. Requieren alta resolución, posición de micrones, en tiempo de nanosegundo y en energía en 1%. Alta ejecución para tiempo y disparo. Resistente a la radiación ya que los protones viajan en todo momento. Sistema integrado completo. La parte electrónica tiene que ser rápida, resistente a la radiación, de alta definición, miniaturizada. En esto tenemos que hablar del ASIC y el FPGA, que son especificaciones de aplicación de circuitos integrados y matriz de portal de campo programable.
So now Chile had just started 1 year ago. India has been working for last 25 years. So just I want to tell you that you see in different detectors we have contributed at different point of time, and at present we are spending about 6 million Swiss franc for the upgrade of from the Indian side. The total upgrade cost is 250 million Swiss franc. So it takes time for us also to be there. When we started with only pre-Sauer and outer hadronic calorimeter, but with time the community grew up and we are participating in much more. So in the same sense, the Chilean group over the time should grow up and then they can also take the lead.
¿Cuáles han sido las contribuciones de la India al detector CMS? Estas son algunas de las contribuciones que se ha hecho hasta el momento. Durante los últimos 25 años, comenzamos con 2 detectores y actualmente se han contribuido con más de 67 partes para el detector, además de la contribución monetaria para su mantención y actualización. Esto es algo que ha tomado tiempo y esperamos que algún día Chile pueda contribuir de la misma manera y ser parte íntegra como lo es India.
So this is a GEM detector on which we are working, on which Chile group is also working. And that's why I'm showing you this picture. So we have made 17 detectors like this. This is our lab in Delhi. We just took the picture. And we have sent it to CERN, 17 of them, and they are mounted in there. So GEM is a micro-pattern gas amplification detector. So when charged particle passes through it, it leaves the track, and you can see it. Now, University of Tarapacá Arica group has joined the GEM effort with Dr. Salini Thakur as the leader, a postdoc and an engineer. and they are working on hardware, the detector part, both in Geneva and in Delhi. They are also working on how the detector is performing. So it is already mounted, there are data, they are checking the data, and they are working with us. And now they have also joined Higgs boson effort for the search and the properties of Higgs boson.
El detector GEM. Este es un detector de amplificación de patrones de gas para rastrear muones. Estos son los detectores construidos en nuestros laboratorios en Delhi. Se han hecho alrededor de 17 de estos detectores GEM y se han diseñado y creado en el laboratorio. Se ha realizado una colaboración estrecha con Micropack para el desarrollo de la próxima generación de placas. La Universidad de Tarapacá, bajo el liderazgo de la profesora Chalini Thakur, lidera el grupo que está trabajando en la actualización del hardware en CERN y realizando el análisis del bosón de Higgs, el cual es uno de los análisis más desafiantes.
So when we make the detector, we don't only make it for the research. What is the feedback? What is the spin of the detector? So I'm not going to go into detail. This one is the detector, GEM detector. You see there is a key, there is a coin, things like that, various metallic stuff. Then you have X-ray, low energy X-ray, you pass it over it. You take the data, you collect the data, you see their pictures coming here. Now what you can do, that it is the thickness, gram per centimeter square. So the density of the material you can see with the heat density. Now what is the use of it? This is very nice to see because it is a paper published, so you get a paper. But more than that, these days smuggling, transportation of nuclear elements, smuggling of nuclear things, these are happening in various places in the world. You can build large GEM detector, you can put it on the top, you can put it on the bottom, the truck goes through it, and you can take the scan of it. It might take a minute or two with the very fast scan, and you can see that whether they are smuggling anything illegal or not. If you are smuggling wine, it will not be caught. But if you are smuggling uranium or something, it will be caught. So the detector also has a spin-off for the society.
¿Cuáles son los spin-off o usos más prácticos? Uno de los usos que se les puede dar a estos detectores es que al pasar elementos por rayos X y analizarlos, pueden ver el grosor y densidad del material. Un material con mayor densidad podría aparecer como caliente y podría ser identificado como uranio. Y esto puede medir distintas sustancias y ser utilizado para la seguridad nacional. Un material radioactivo o para revisar si está cubierto de plomo o algún material que podría ser detectado antes de ingresar al suelo nacional.
So I know it is 1 hour now, so some snapshot of physics. This is a Higgs boson which decays into 2 photons, 2 light-like particle, photon. It is a very clean signature, but out of 1000 Higgs, 1 decays into gamma-gamma, but you can reconstruct the mass very nicely.
Aquí pueden ver un bosón de Higgs. La masa puede ser degradada en gamma-gamma, pero todo esto puede ser reconstruido fácilmente gracias a nuestros equipos.
This is the same Higgs boson which goes into Z star, which goes into 2 electron, 2 muon. So the green ones are the electron, the red ones are the muon. You can reconstruct the mass of red ones, you can reconstruct the mass of the green ones, and you can reconstruct the mass of Higgs. So again, very clean signature, so that's how you can reconstruct the Higgs mass.
Aquí hay una imagen clara de cómo se ve un bosón y pueden ver electrones y protones disparados en distintas direcciones. Todos estos pueden ser reconstruidos para su posterior análisis.
This is a Higgs boson going to ZZ. 1Z goes to 2 mu, 1Z star goes to 2 mu, you have 4 muons. Now you make permutation combination of that. Z mass is known at 91 GeV. So one permutation will give you the Z mass, other 2 will give you Z star. You reconstruct the Higgs boson. You can very precisely reconstruct the mass to 1% precision.
Esta es la imagen de otro evento en el cual se puede reconstruir la masa de un bosón a una precisión increíblemente fina.
So now this shows you that when you reconstruct the mass in diphoton channel and the 4 lepton channel, This is just the signal over signal by background. So this is just the background, and you see there is a bump at the mass of 125 GeV. So this is jet boson 91 GeV, and you see here is the mass at 125 GeV, and that's why you see that there is event signal above the background, and then you know that you have discovered here, you have discovered in this channel, you have looked into other channels, and then you have to see that you discover at not only in this different channel here, but also in CMS and Atlas experiment.
¿Cómo es la masa del bosón de Higgs? Esta es la masa que se puede detectar con una señal sobre señal y puede ser apreciada en el fondo aquí. Cada uno de estos peaks equivale a un evento de 150 GeV, haciendo posible que el bosón fuera descubierto en más de un sensor.
So the Higgs boson was discovered in 2012. We didn't know about this particle. Now we know about this particle. This is the two spokesperson at that time, CMS experiment, Atlas experiment. The discovery was announced on 4th of July, 2012. The economists wrote a giant leap for science. The Science magazine wrote breakthrough of the year. These two gentlemen, Englert and Peter Higgs, they were together in this room, and they got Nobel Prize in 2013.
Estas son partículas de campo. Aquí hay una fotografía en la que se ve la actual directora del CERN, quien ha sido electa para llevar un segundo mandato. El doctor Candela, portavoz del experimento, viendo los flujos de datos, el cual fue calificado como un evento de importancia mundial. Varias portadas de revistas lo describieron como un gran salto para la ciencia y un avance increíble en el año. Estos caballeros que están representados aquí ganaron el premio Nobel en el 2013.
Now for the girl student, female students. This lady, her name is Fabiola Ganotti. She was the spokesperson of the Atlas experiment. For last 7 years, she is the Director General of CERN. The first woman to be the Director General of any major lab in the world, and CERN is the largest lab. And she is the first person, first Director General of the CERN to get 2 terms. Everyone got 1 term, she is in her 2nd term. So for the female students, it is very important that you are no less than the male, and the world is the limit. And here is an example.
Un detalle que cabe destacar, sobre todo para las estudiantes mujeres, es que ella es la primera mujer que ha sido electa como directora del CERN. Este es su segundo periodo y esto les demuestra que el cielo es el límite.
So now, many of you know that the Higgs boson is also called God particle. Okay? So why it is called God particle? This gentleman is Leon Lederman. When I went to Fermilab in 1987 to do PhD, he was the director of that lab. So we were working on the tevatron. The Higgs boson was not being found. So he was writing a book, and he told his publisher, the goddamn particle, we cannot find it. So the publisher told, if you name the book the God particle, it will sell a lot. So that's how the Higgs boson is also called the God particle. And this is just a joke. Say God particle once more, God that time, God particle. Okay? So that's how the God particle comes. It has nothing to do with religion. Okay? It has nothing to do with religion.
La partícula de Dios. ¿Qué es la partícula de Dios? Este señor es Leon Federman, quien fue el director del laboratorio de Fermi. Estaba escribiendo sobre esta partícula en particular y durante muchos años no podía descubrirla, por lo cual la llamó la partícula maldita. A petición de su editor, cambió el título del libro a La partícula de Dios, que tiene una denominación más comercial, y así el bosón de Higgs ahora también es conocido como la partícula de Dios. No tiene absolutamente nada que ver con religión.
Okay, so when the discovery of Higgs boson was put, Physics Letter B is the most prestigious journal in Europe. They wrote it as the, one of the greatest scientific discovery of the all time, and these are the 2 pictures from CMS and Atlas.
Descubrimiento del CERN del escalar bosón. Aquí tenemos el descubrimiento que lleva a las páginas principales de revistas científicas y varias revisiones calificándolo como el descubrimiento científico más grande de todos los tiempos. Acá tenemos imágenes del colisionador y su ubicación en el mapa.
So now we are studying the property of Higgs, and I'm not going to go in detail. We have measured its mass. You see mass in the gamma-gamma channel, mass in the Z-Z channel, so the average mass. We have measured its width, and these are according to the information that we should have. So we are measuring properties of it.
No voy a dar demasiados detalles sobre las propiedades del bosón de Higgs, pero aquí pueden ver que ya hemos medido su masa y el tamaño del bosón a una precisión muy alta. Y esto nos dice que estamos entendiendo de manera muy detallada esta particular partícula.
This is the spin parity. So the particle have a spin either 0, 1 or 2. Parity is plus or minus. If plus parity is when you look yourself in the mirror, do you look the same or you look different? So it is the positive and negative parity. And its Higgs boson has a parity 0 plus. And you look here, it is the 0 plus, and this is the 0 minus, and it is pointing towards 0 plus. And this is 2 plus and 0 plus, and it is pointing towards 2 plus. So the particle that we have discovered has the property that is expected. Okay?
Pero de su descubrimiento tenemos que medir su masa, tamaño y otras propiedades. Así que, como sabemos, una de las características del bosón de Higgs es que es una partícula escalar con una órbita cero, asperidad positiva, y aquí pueden ver un spin positivo, spin negativo con características específicas, lo que la hace una partícula densa.
Okay, so now top quark is the heaviest of the particle, 172 JeV. So we are looking at how the top quark interacts with the Higgs. So this is the production. You see TTH event, and again signal over background. So it is mostly you see signal over background matches. Here you have little extra, and this is what we get over the standard model expectation. You see it should be 1, but it is 1.26 with large error. So we need much more event to understand that. But what it means that if it is different than 1, that means there may be some new physics there. So you need to measure it to a very high precision. Okay? It should be like 1.00 or 02 plus minus 0.01, 0.02. So we need many more events.
Empalme Higgs a quark superior. Así es como los bosones son producidos. Esta partícula es la más pesada y asume que su empalme con los quarks de orden superior podría fácilmente ocurrir. Aquí estamos viendo la señal de fondo en algunos eventos son observados, y esta señal que hemos descubierto en el modelo estándar que se ha dado por 1.26 de gran amplitud y es cercano a 1. Cualquier medición menor a 1 podría significar que se necesita un nuevo tipo de física.
So now I will skip the two slides, 58 and 59. So CERN has, as you can see, from 2010 to 2022-23, it has published various papers. India has about 2.5% PhD scientists out of that 1,500 that we pay money. India has large number of students, so we are able to contribute into large number of papers, and we have submitted up to 1,200 papers till now.
Publicaciones del CMS. Actualmente y durante lo que va de año se han publicado más de 1.200 artículos. Posee un gran número de estudiantes de doctorado y de postdoctorado que contribuyen a la escritura de estos artículos y la publicación de estos.
So one thing I would like to tell to the students, especially the master's student, the undergraduate student, to get involved with these projects, and I would like to tell the authorities that it is very, very important to involve students, because the professors have to teach, professors have a lot of other work to do. So if you have PhD students, it is very, very helpful for the university. So PhD program in English is very important here.
Los programas de postdoctorado y de doctorado son algo muy importante de producir en las universidades, pero también los estudiantes de maestrías y de pregrado tienen un lugar importante, ya que gracias a ustedes es que se tiene que proporcionan personal para poder continuar con estos experimentos.
So this is CERN. This is a picture of Nataraj. Nataraj is dancing Shiva, a Hindu god. So it is said that basically creation, preservation, and destruction all lies in his hand. So here is the head of the Department of Atomic Energy from India, Anil Kakodkar in 2004, CERN Director General and Ambassador of India in Geneva. They are all there, and this is a gift to CERN from India, and here it is written in Sanskrit and in English what it means.
Esta es una imagen de Nataraj, que es la chiva danzante. Ella es una representación de la creación y la destrucción. Este fue un obsequio del Departamento de Energía Atómica de India al CERN, y aquí hay algunos representantes diplomáticos junto a los directivos del CERN.
This is CERN globes. Just outside the CERN main lab, there is this structure. This goes like this, a very large steel thing, but when you take the picture, it comes like. So you see it has written in Greek, it has written in Arabic, different languages, what the different civilization has contributed. So I will tell you from what is from India. The infinite series was given by Madhav and Sankara, two mathematicians from India. The 0 and negative number was given by Brahmagupta from India. The length of a year was given by an Indian mathematician Bhaskaracharya. So they are trying to give importance to all the discoveries and from different parts of the world, and not only talk about themselves. So it represents the global achievement over time that has happened.
Afuera del CERN existe este orbe en el cual se han descrito todos los más grandes metas y descubrimientos que ha hecho la humanidad. Acá hay tres específicos, por ejemplo, que son algunas contribuciones que ha hecho la India, que es como conceptos matemáticos de los años bisiestos, noción de cero y de negativos.
So, summary, I know it has been hour and a half because of the translation. So particle physics is the most fundamental and one of the most interesting branches of science. The energy frontier, the intensity frontier, and the cosmic frontier complement each other. So here is the energy frontier with accelerator, cosmic frontier with the telescope, intensity frontier with very high energy beam. The smallest and the largest, so smallest particle, the largest, you see the galaxies and all the stars are intertwined and provide the answer to the same basic question, how did the universe start and how it has evolved. But we still know very little about the universe. Most of the universe, 95%, is not known. So there is a lot to explore, and the students could be part of it.
En resumen, la física de partículas es una de las ciencias más fundamentales e interesantes del área de las ciencias. La frontera de la energía, la intensidad de las fronteras y la frontera cósmica se complementan mutuamente. Lo pequeño y lo más grande están entrelazados y proporcionan respuestas a las preguntas más básicas. Hay aún mucho por descubrir de nuestro universo. 95% de este es desconocido y está aún mayormente inexplorado. Sean exploradores.
So I would like to thank PAIR, the Indian taxpayer, the funding agency, and CERN for providing the opportunity. I would like to thank all of you and the Instituto de Alta Investigación, University de Tarapacá, for this invitation and for visiting Professor. Muchas gracias. And David, if students have questions. Sure, please.
Preguntas pueden hacer en español y nosotros las traducimos. Sin miedo. Sin miedo. Todas las preguntas son bienvenidas.
Please.
Well, thank you. Well, thank you very much for your great conference, and it has a lot of information, and you reduce in 1 hour, a little bit more, perhaps. And thank you for that. Following with the relevant ladies, let me invite to this room Emily Netter.
Who?
Emily Netter.
Okay.
You know the Netter
Emily
theory.
Noether, yes.
Yes?
Yes,
You know that, of course.
Yes, Emily
So
Noether.
which relate symmetry
Yes.
with conservation love.
Exactly.
So you you see, when you talk about the study of this Nobel Prize about this Higgs boson,
It is with the electroweak symmetry breaking.
It's appear broken symmetry.
It is.
So what is the meaning of that?
What is the meaning of electroweak symmetry? That the electroweak symmetry breaking means that the electroweak bosons above a certain energy scale are all massless above a certain energy scale, but below that scale, the photon has 0 mass, the W and Z has very high mass, so that is what the broken symmetry means. Okay?
Hello.
Hello.
So I remember one of the questions. The first question was the nature of dark energy. And you said that it consists about three-fourths of the universe?
Roughly 70% of the universe.
Oh.
Yeah.
But before that, you said that we still don't know what dark energy is?
Yes. So we know that the universe is expanding. Fine. So its size is increasing, the size of the universe. So there is mass and energy. Wherever energy is there, you can do mass. But we do not know what is this dark energy is. When we observe supernovae, okay, we see that as they go further, they move faster. So that means it is expanding. But we do not know what it is. There are various speculations, but none of them are. I will not like to tell that I know about dark energy, because no one knows about dark energy. Okay? So that is completely open. About the dark matter, we know there is dark matter because it is matter, so it has gravitational pull, but we have not found it. There are two kinds of experiments. One is the kind of experiment we are doing. We are also searching dark matter. We have not found it. And then there are cryogenic dark matter. If the dark matter particles are very light, then they are these are under the mountains, where if the dark matter gets produced, let's say in the universe, they go through it, a strike there, and then there are phonon interaction, but we have not found anything.
Yeah, thank you.
Yeah.
Voy a tratar de traducir un poco lo que dijo el profesor, no al mismo nivel, por supuesto. Lo que dice el profesor es lo siguiente, dice que en general solo conocemos el 5%, el 95% no se conoce, por lo tanto se cree que en realidad eso se puede atribuir a materia oscura o a energía oscura. Se sabe porque el universo se está expandiendo. Entonces, de alguna manera, esa es la clave de decir, bueno, tenemos que tener algo diferente. Y hay diferentes tipos de experimentos en los cuales se está realizando eso. Entonces, dependiendo de qué tipo de materia es, uno podría tratar de encontrar. Eso es más o menos lo que trató de decir el profesor. Thank you, professor.
First of all, thank you for sharing your knowledge with us. I have a question.
Sure.
About why you think it was so important to mention the elements, water, ether, and...
Oh.
Because...
It is why it was okay, very good question. It is important, see, when people have some curiosity in themselves, then only they go to look for the thing. So we have to understand that the science doesn't begin out of nowhere. Suddenly we don't say we are scientists, we are going to do something. The quest has been there for time immemorial. When the humans civilized, the civilization where they had enough food, they were by the river, so there was enough food, meat, everything. They had knowledge, they could read, they could play music. So people have this quest to know what the universe is made up of. Think about 2,500 years ago looking at this star. You don't know what this star is. So, but some stars were always fixed if you look from your place in the night. So people must have thought why they are always fixed, and they thought about it, they gave the theory. So in the same sense, they wanted to know that what is everything is made up of. But at that point, they knew about water, they knew about air, they knew about fire. So these are the things they thought made everything. It may have some philosophical, religious component. So you have to know that where the quest was, but that is not pure science, that is philosophy. And science comes out of that. So that's why I mentioned, because it is very important to know that what we do things today, it has been thought about, in past also.
El concepto principal viene de lo que conocemos, en este caso los elementos básicos, agua, tierra, fuego, aire, y es en base a esos que se crean conceptos filosóficos y religiosos que luego hacen que nosotros empecemos a investigar qué es lo que sigue. No nacemos diciendo somos científicos, tenemos que tomar bases y para ello está esta mención que se acaba de hacer.
Thank you.
First of all, thank you for all the knowledge. It's very interesting. My question is, you mentioned smaller black holes?
Yeah, micro black holes.
And
yes, so let me.
How it's produced?
Okay.
Is no represent
yes.
any damage?
So there are theories which says that if extra dimension exists, in proton-proton reaction, micro black hole could be produced. These will be very micro. And when they decay, they will be symmetric decay. Like if you have a sphere, it will be equally distributed everywhere. So these are the theory which we are testing. We have not found it. Okay? But even if it is right, trust me, with these micro black holes, we are not going to vanish.
La teoría de los microagujeros negros son solamente eso, teóricos. Cuando se colisionan protones con protones, existe la posibilidad de que estos puedan ocurrir, pero hasta la fecha no ha pasado. No hay nada de qué preocuparse, no se va a destruir el mundo gracias a ellos.
There is one in back. You tell a student if they are comfortable speaking in Spanish, then David can translate, I can answer.
Si hay alguien que quiere preguntar en español, podemos hacerle traducción, no hay ningún problema.
Yeah, I have a question related to protons. You said there are like 100 billion protons at once, but yeah. And my question is, how do we take one proton, two protons, and put them all together and then throw it into the...
Oh, okay. So you saw those 5 of those accelerators, 1, 2, 3, 4, 5 that I showed you, right?
Yeah.
So what we do, we take hydrogen atom and we strip the electron out of it. Mm-hmm. So in hydrogen atom is a proton in the nucleus, an electron revolving around. You strip the electron, so you are left with naked proton. So you keep on doing this process very fast, okay? And so you collect a lot of proton, then you accelerate them together, and then you make a bunch of 10 to 11 proton.
But how do we, protons repel each other?
Exactly,
yeah.
Protons repel, exactly. So what happens that you have the protons, a billion of protons there, and they are going through the magnetic field, which focuses them, okay, which squeezes them, and then there are area where there are no magnets, so they also repel. So in the very beginning when I said that there are 9,300 magnets in which there are dipole, quadrupole, sextupole, octupole. So sextupole and octupole's job is to correct their orbit, and then dipole bends them, and quadrupole again focuses them into very small area.
Okay, thank you.
Okay, so the question is essentially, la pregunta esencialmente es ¿cómo hacemos con los protones, ¿no es cierto?, que están circulando? Entonces el profesor de alguna manera explica que bueno, hay toda una circuitería, es decir, pasamos por distintas etapas donde se aceleran los protones esencialmente, y claro, nuestro estudiante nos dice, bueno, pero en realidad se repelen. Entonces, ¿cómo los podemos de alguna manera volver a juntar? Entonces, hay distintos aparatos, que son los polos para acelerar, los cuadrupolos para ir juntando, y así con este distinto set de aparatos logramos de alguna manera tenerlos todos juntos, tener el haz y hacerlos colisionar en algún punto. More questions? ¿Más preguntas?
Ya, quería saber qué es la antimateria. Actúa con la materia. ¿Ahora sí? Ya. ¿Qué es la antimateria y cómo esta puede interactuar con la materia?
He like to know what is the antimatter and how this antimatter interact with our matter.
So for example, if we look at an atom, proton, electron, proton and neutron are in the nucleus, and then electron is there. So initially it was thought that they are all proton matter, because we knew about electron much before we came to know about E+, which is positron. So all particles have antiparticles. All particles have antiparticle. So proton is the particle, proton P bar, okay? Proton with a negative charge is a antiparticle, okay? So what will happen? You take a lot of proton, you put a target, okay, beryllium, carbon, something, it will produce a lot of other particles. In that also you can produce antiparticle, which is the antiproton. But in the cosmic ray, the ray that comes from, we get both particle and antiparticle, because cosmic rays are extraterrestrial rays which comes to our galaxy, and then it collides at the surface about 15 kilometer high where the atmosphere is, and it produces various kind of particles, and antiparticles are there. So every particle in the universe has an antiparticle. So there is electron, there is positron, there is proton, there is antiproton, there is neutron, and there is antineutron. Okay, there is neutron which is made up of U, D and D quark. Antineutron will be made up of U bar, D bar and D bar. So I said there are 6 quarks. For every quark there is an antiquark. That's how the universe is. Okay, every particle has an antiparticle.
Muchas gracias.
Lo que dice el profesor esencialmente que la antimateria, dada la materia, tiene distinta carga. Entonces, si el electrón tiene carga negativa, el positrón tendrá la carga positiva. Y lo que dijo es que cada partícula, cada quarks, tiene asociado un antiquarks. Es decir, por lo cual podemos tener un protón, un antiprotón, podemos tener un electrón y un positrón, podemos tener un neutrón y un antineutrón, porque está formado dentro por quarks.
¿Más preguntas? Sí, acá. Disculpe.
Okay.
Quería preguntarle a usted si cree que durante las próximas décadas o dentro de este siglo el ser humano podría ser capaz de entender en su completitud la teoría de la gran unificación, o si está muy lejos de nuestro alcance.
The question is if in the next decade or in the next few decades the human being can understand the theory of great unification.
Grand unification. I will be very happy that that in my lifetime, which is, means I'm a senior person, so I don't know how long I will live, 10 years, 20 years, something like that. But if in my lifetime I can understand the theory of grand unification, it will be great. There are experiments going on to learn about grand unification. Grand unification will not be learned at these there. There are neutrino experiments going on in Japan and in America. One is called Hyper-K, and the another one called is Dune. Hyper-K is in Japan, Dune is in America, in South Dakota. So there are experiments where if they see that the proton decays, proton has a lifetime of 10 to 34 years. The universe is only 10 to how much? It is 13 billion years, fine. So 10 to 10 years. So universe is 10 to 10 years, proton has a lifetime of 10 to 34 years. So if we can understand that the proton decays, then we can see that we have seen a signature of grand unification. Many experiment has been done, but we have not seen it. Okay? But yes, that's a very interesting field.
Es un tema muy interesante. El profesor quisiera tener la oportunidad de poder ver este proceso de gran unificación en el CERN. En el CERN no es posible de observar este tipo de procesos. Hay dos grandes experimentos que se están realizando, uno en Estados Unidos y otro en Japón. Esencialmente, para poder ver la traza de la gran unificación, se necesita entender el decaimiento del protón. El universo conocido se considera que tiene, en términos de tiempo, 10 a la 10. El decaimiento del protón es 10 a la 32. Por lo tanto, claro, ver el decaimiento del protón y ver la traza de esta caída es realmente un proceso difícil, pero se está buscando. Más o menos.
Thank you. There is a student. First, this is student.
Good morning, Professor.
Good morning.
I would like to ask why the gravity force is a weak force.
Why the gravity force is a weak force? If I can answer that question, I will be buying my ticket to Stockholm. So gravity force is the weak force. You see G, gravity is some constant times force is equal to gravitational constant m1, m2, r square. So for example, it is for the heavenly bodies, and there you can look at it very strongly, but not for small objects. And honestly, I do not know the answer to your question. Okay?
Thank you.
If I knew it, I will go to Stockholm. So
El profesor no tiene la respuesta a su pregunta, pero es una pregunta muy interesante. Yo creo, debido al tiempo, podemos pasar a, tenemos un cóctel preparado para todos ustedes. Realmente me gustaría volver a agradecer al profesor y dejarle algo muy interesante. Nuestra universidad está dentro de las dos más grandes colaboraciones en el CERN. Ustedes como estudiantes tienen la posibilidad de estar ahí. Úsenla. Agradezcamos al profesor.
Muy bien. Muy bien. Muy bien, a continuación, Profesor Brajesh, the substitute rector, will present him with a GIF. Please.
okay, thank you, thank you, thank you.
Estimada concurrencia, de esta manera la Universidad de Tarapacá está dando término a esta relevante charla magistral y se invita a los presentes a pasar a compartir un refrigerio. Muchas gracias y buenas tardes. No, ni tan bilingüe.